All of you guys should have been, you should have turned in your homework on Friday, right? So that was mission complete. If I'm not mistaken, a week from Wednesday, so not this Wednesday, but the week following that, your first project milestone is due. So make sure you've looked at the requirements for that. Like I've mentioned last time, I think I mentioned this last time, but I can't remember. You shouldn't really stress out about the milestone. Nobody can fail the milestone. Nobody gets less than perfect on the milestone unless you're like really not turning anything in. So the milestone is there so that you can think of an idea, and it's a kind of a forcing function just to get you to write it down. If your idea is not going to work, if we read it and we think, wow, it's going to be difficult or it's not really appropriate, then we'll tell you. That's the purpose of the milestone. So it's just a check that you're on the right track. So don't freak out about it too much. It's just supposed to be 2 pages long. Take a look at the guidelines on the website for that. How many people do not have project partners at this point? Just so I can see a show of hands. Okay. Maybe you guys should raise them higher and look at each other. That might help. You guys stop raising your hands. Are you guys going to work with each other now? Or maybe. Okay, that was successful, at least in some part. So there's a few people here. If you guys haven't already, you can email the Piazza group to try to find partners for that, or just post a message there. If you want to come see me after class, I'm not quite sure who raised their hand, but if you guys want to come see me after class, we can try to help facilitate that, or you guys can, if you remembered who you were, you can just meet up with each other. So we're looking at hopefully groups of 2 or 3 for the projects. Are there any questions about the project or the homework or anything else like that at this point? Yeah. Homework 2 is going to be posted hopefully in the next couple days. So by Wednesday, hopefully. All right. So you guys have had a lovely cast of characters in my place the last 3 lectures. So you got to hear Nicole, and then Javier and Mattia, and now you're back to me, and you'll be forced to listen to me for a little while. So today we're going to talk about subgradients, and I am particularly excited about this topic because I feel like this is one of the more empowering things you'll learn in this class. So remember, I said that about convexity too. I said that when we talked about convex functions and convex sets, that you'll find that once you kind of learn the rules, it's very empowering. That's also true about subgradients. And to some extent, subgradients are, convexity, I feel like most people who work in the area of statistics, machine learning, control, engineering, they kind of know. But subgradients are even more, I'd say, even less well known in general. So by gaining this skill, you'll be even more unique in a sense. If you're able to handle subgradients very well, then you'll be able to solve problems that other people can't really understand at the same level that you can. So it's a very, I think it's a very neat topic. It's also not one that's always covered. So like I mentioned before, in the Boyd and Vandenberg textbook that we use as kind of a supplementary text, they don't even talk about subgradients at all. So the reference for this, you can think of the class notes as the definitive reference, but we also put some references at the end so that you can check some of the more mathematical textbooks, like the Rockefeller book I mentioned for subgradient supplements. So last time, I was told, I wasn't here, but last time you guys did gradient descent. And the problem that you guys considered was to minimize a convex and differentiable function without constraints. So that was the first of our algorithms lectures. And now we're in an algorithms unit. So we're going to talk about subgradients today really as a means for us to learn. Really, we're talking about it so that we can learn subgradient method next class. So gradient descent, remember, chose an initial point. Here we're thinking that, like I said, the function's unconstrained and its domain is all of Rn. So we just chose some initial point in Rn. And we repeated this step over and over again, which just computed the gradient of the criterion f at our current iterate. So we call that xk minus 1. And moved in the direction of the negative gradient from where we were. So we were at xk minus 1. We take a small step. The tk is some small positive number here. times the negative gradient, and that's our new iterate, xk. So it's kind of like going downhill on the function f by following its negative gradient. The step sizes were chosen to be fixed and small. That was one rule that you learned. For example, if they were less than or equal to 1 over the Lipschitz constant of the gradient of f, we learned that this method is provably convergent. In fact, I think you proved that in class. Or by backtracking line search. That was another way of choosing the step size. Even more so than just proving that it's convergent, you guys actually proved that if the gradient of f is Lipschitz, and the step sizes are appropriately chosen, either by this rule or by backtracking, then it converges at the rate 1 over epsilon. So what we mean by that is that if you fix me an epsilon, in order to achieve a suboptimality bound of epsilon, which means that I want to make sure that f of xk minus the true optimum f star is less than or equal to epsilon, then I must take on the order of 1 over epsilon steps. Okay, so that's how it scales with the desired suboptimality bound. And we'll see what next time how this compares to something like subgradient method or other methods that we learn in this unit. So this will be kind of our baseline for something we know we can achieve in a simple problem, smooth convex function. So what are the downsides of gradient descent? And to recap, it requires f to be differentiable. That was one of its bigger limitations, right? We can't handle non-smooth convex functions. It was just for differentiable functions. Next lecture, we're going to talk about that. So we're going to talk about how to extend the gradient descent method to convex but non-smooth functions. That's called the subgradient method. That's what we'll use. Another downside is that it can be slow to converge. So typically, we think of gradient descent as having cheap iterations. All we have to do is compute the negative gradient and then follow it. But it can be slow to converge. And we have to use a lot of iterations before we achieve our desired level of accuracy. And we're going to address that 2 lectures from now when we talk about acceleration. Any questions about gradient descent? Okay, so that was last time. This time, like I said, we're going to learn subgradients, which are in a sense the mathematical meat behind subgradient method. And actually, they're going to be very important for a lot of the optimality conditions that we learn later in the course too. So this is definitely a really fundamental topic. So we're going to learn subgradients, some examples of subgradients, some of the calculus of subgradients, just like we learned calculus of convex functions. And lastly, we'll talk about some optimality characterizations that we get out of subgradients. So let's just dive right in. So for a convex and differentiable function, remember this was this was a necessary and sufficient condition for it to being convex if we had a differentiable function f. And in words, it says that the linear approximation to the function has to always be an underestimator of the function. So in other words, if you give me an x and y that are in the domain of the function, and I look at f of y, and I compare it to the linear extrapolation that I would have gotten if I started at x and built a line around the gradient of f of x, that's this part right here, then the linear extrapolation, or the tangent line at x, has to lie below the function. That was this picture. Remember, if we have x here, and we look at any other point y, and we look at the value of the function, right? So this would be f of x, this would be f of y. Then we saw that if we took the tangent line, or the first order approximation, all of my pencils are breaking. Third time's a charm. If you took the first order approximation to f at x, then that would underestimate the function. Right? So this line here is exactly by this formula. I'm just drawing it in an illustration in one-dimensional case. So what's a subgradient? A subgradient is a generalization of this idea to a non-differentiable function. In the sense that, a possibly differentiable function, but we're not going to assume that it's differentiable. So for a convex function, we say that f has a subgradient at a point x. So you fix a point x. After the subgradient at a point x of g, where g is just some vector in Rn, if the linear extrapolation given by g is an underestimator to the function. So in other words, if we were to build a line at x where the slope, in a sense, is dictated by g, remember this is an Rn, so it's really it's a plane. But this is exactly the concept that we think about in the differentiable case. Then this serves as an underestimator to the function. Okay, so it's the value of g that gives us a first-order approximation that underestimates the function. So this always exists for convex functions. That's one thing that's very nice. Subgradients always exist at any points. And if f is differentiable at the point x, then it only has one subgradient uniquely, and that's its gradient. Okay, so it's a strict generalization of the idea of a gradient for a convex function. So let's just absorb that for a second, because it's a rather important point. Right? If I'm just going to repeat what I said. If f is convex, then there's only one g. If f is convex and differentiable, then there's only one g that makes this true at the point x for all y. And that's to take g equals the gradient of f at x. Okay, we know that from the definition of convexity for smooth functions. If f is convex but not differentiable, then there could be multiple g's that make this true. So there could be multiple subgradients of f at the point x. Right? There could be multiple g's that make this true for all y. They give us some kind of under approximation. And you can think about this picture. Right, let me take a function. This function is convex, but it's non-smooth. This is the point x. There could be multiple slopes in the 1D case, right, that give me an under approximation to the function for all y. So those are all be subgradients of the function f at x. So actually the same definition works for non-convex functions. So non-convex functions can have subgradients, but they need not exist at every point. That's an important distinction also. Okay, so the concept of a subgradient is actually not special to a convex function. It's just that for convex functions, we know that they exist. So let's just do a very simple thought experiment. If I had a smooth but non-convex function, does it need to have a subgradient at every point? So we know that for convex functions that are smooth, the subgradients are just the gradients, right? There's only one subgradient at any point, and that's the gradient. I'm asking, is that true for non-convex functions? I see some people shaking their heads. Why? Do you have an example that shows that's not true? What's that? Minus? Okay, yeah, that's a good example. So, right, and in this sense, the gradient, for example, at 0 would be not an under-approximator, but an over-approximator to the function. Right, so that's just one very simple example. How about this one? It's another one where it's not necessarily a concave function. This function is x cubed, for example, right? It doesn't have a subgradient at 0. Right? There's no single slope that will give me an under-approximation to this function everywhere. So you may equate subgradients with gradients in your mind when we're talking about convex functions. That's perfectly fine. That's in fact exactly what they are. But for non-convex functions, they can be smooth and still not have subgradients. Okay? All right. So let's go through some examples. We've already seen a couple kind of picturesque examples there. Let's talk about f being the function that just gives me the absolute value of x. So it's univariate. So this is what it looks like. When x is not equal to 0, this function is differentiable, right? So we know that its derivative has to be its subgradient uniquely. So it only has one subgradient away from 0, and that's just the sine of x, because that's its derivative. So it's either 1 here or minus 1 here. At 0, it has a bunch of subgradients. In fact, the subgradient of f at 0 can be anything in between minus 1 and 1. Right? How do we see that from the picture? Any line of slope minus 1 or 1 will give us an under approximation to the absolute value function if it's forced to pass through 0. How about mathematically? Right, mathematically, we said that f of y has to be bigger than or equal to f of x, plus, in the univariate case, it's just going to be g times y minus x for all y. So if g satisfies this at the point x, then it's the subgradient of f at x. So let's just think of this example. Y has to be bigger than or equal to the absolute value of x, but x was 0 here, right? So 0 plus g times y minus 0. So what values of g make that true for all y? Anything in between -1 and 1, inclusive, right? So I just came straight from the definition, but you can also see it from the picture. Okay, a little more sophisticated would be the Euclidean norm, L2 norm, in Rn. So here's a picture of what it looks like in R2. You can see that this function isn't differentiable at 0, right? It's a convex function. We know that already because we know that norms are convex. Away from 0, it is differentiable. Its gradient is just x over its norm, right? We can just do kind of a standard calculus to see that. So this is its only subgradient then, because it's differentiable away from 0. When x is 0, it has many subgradients again. And this one's a little harder to see from the geometric perspective. I mean, visually it's harder to see. But you can draw yourself a picture and try to convince yourself that it's true. Let's just follow the definition for now. So we want to prove that, just go back to this, right? Where we're using the Euclidean norm. The absolute value of y has to be bigger than or equal to 0 plus g transpose y minus 0, right? Because we're talking about the Euclidean norm at 0. So what values of g make this true for all y? Think about the Cauchy-Schwarz inequality. What values of g make that true? You guys know this one. The answer's on the slide, right? I think people are just tired. Anything that has Euclidean norm less than or equal to 1, right, would make this true. Nod your head if this makes sense. I just want to make sure we're all on track. Okay, good. So how about the absolute value? How about the L1 norm of x? So a little bit different than the Euclidean norm. Here's another picture of this just in R2. You can convince yourself from this picture, but also from thinking about it, that this one's actually not differentiable along any coordinate axis. Not just at 0, but any of the standard bases axes, or standard coordinate axes, it's not differentiable. So let's talk about the components of the subgradient. Right? Subgradient's a vector. It's easier in this case to characterize its component. When the ith component of x is not equal to 0, you can argue that the gradient in the ith component is unique of the L1 norm, right? Because the gradient would just be the sine of xi. Or sorry, the gradient exists in the ith component. The partial derivative exists in the ith component. So therefore, it's only going to have one, a unique ith component of the subgradient. And that's going to be the sine of the ith component of x. Okay, and if the ith component is 0 of x, then the ith component of the subgradient can be any element between -1 and 1. So this is from the exact same kind of intuition we saw for the L1 norm, just for the absolute value function. For the L1 norm, just think about the function like this. Okay, and what we're going to learn in a few slides is that if we ask for the subgradients of a sum of functions, convex functions, then the answer is just to sum their subgradients. So we're really just applying this rule that we know about subgradients for the absolute value function to the sum of absolute values. So that's exactly what this answer is, right? I'm just characterizing it component by component. All right, so that's another pretty common one we look at, the L1 norm. A last example, let's suppose that I have two functions, f1 and f2. They're both convex and differentiable, and I'm going to consider the maximum of the two. So we know from our rules that this is a convex function, right? I can take the pointwise maximum of two convex functions that's still convex, but it need not be differentiable, right? Because, for example, just in one dimension, the function could look like this. I could have taken the maximum of two smooth convex functions and gotten something that's non-smooth at a particular point. So let's try to think about this just from the perspective of the picture. and you guys can go home and check that this is true formally in Rn as well. If I'm ever in a region where, say, f1 is bigger than f2, then I claim that the function is differentiable there, right? Strictly bigger. So that would be out here. That's because I know that f1 is smooth, right? In the neighborhood of f1, I know that if you know, for example, that if f1 is strictly bigger than f2, then that's going to be true on a neighborhood of the point x. And so in that neighborhood, the function is going to be differentiable. And in that case, because it's differentiable, I just get a unique subgradient. And the subgradient will be the gradient of f1. So the flip side is f2 is bigger than f1, then there's a unique subgradient at that point, and the subgradient is the gradient of f2, by the same logic. How about if f1 is equal to f2? So this is where it could be non-differentiable. Then the subgradient, I claim, is going to be any point on the line segment that joins the gradient of f1 and the gradient of f2. So let's just think about the picture. That'll be easier one-dimensional case. So let's call this function f1, and let's call this function f2. This is the point x. So let's think about what the gradient of f1 looks like at x. That would just be the what we would get had we witnessed the whole function. The gradient looks something like this probably. And the gradient of f2 at x looks something like, say, that. And now in one dimension, what is the set of points that line the line segment joining these two slopes? What does a slope look like that's on a line segment between those two slopes? So first of all, line segment, we're in one dimension, right? So all we're saying is that the slope has to be between this slope and that slope. So that's really anything here. I'm just saying that the slope has to be anything between the two extremes, the slope of f1 at x and the slope of f2 at x. And clearly, any of these slopes, when they are attached to a line that has to pass through x, is going to give me an under approximation to the function. Okay, so that's just the kind of rationale in one dimension. You can check that it still makes sense in n dimensions just by following the definition of subgradients. Questions? Yeah.
So this might be a stupid question, but why are you referring to it as a line segment? Like, what is that referring to?
Oh, okay. Well, so in Rn, say, right, the gradient is an n-dimensional vector. Right? These guys are both, if I had this example, but in Rn, each of these are n-dimensional vectors, right? So I'm just saying that a subgradient is going to be anything on the line segment joining A and B, which you might write like this. I mean, another way of writing that is that it's in the convex hull of the points generated by A and B. That's just the line segment, right? But in one dimension, this is just an interval. So it's saying the slope has to lie between A and B. That's it, which is what this picture was demonstrating. All right. So the set of all subgradients of a function is called its subdifferentiable at a point. So the subdifferential of f at a point x is the set of all subgradients to f at the point x. So we collect all the g's that make that inequality true that I wrote down. Right? All the g's that satisfy this at a point x, they form the subdifferential. It has a bunch of pretty special properties. Here's one property that's actually, I think it's quite remarkable, and we'll see this kind of thing pop up when we learn conjugates, when we learn duality. We get this property, which is that the subgradient of a function at a point x is closed and convex, and that's always true, regardless of whether f was convex in the first place. So even if I have a non-convex function, its subdifferential at any point is going to be convex. It might be empty. It might be the empty set. That's still a convex set, though, right? So it's always convex. Why is that true? Let's just spend a second to think why that's true. So let's suppose I had G1 and G2 that made this true. if I have two subgradients to the function f at a point x, then these would be two elements of its subdifferential. Now what happens if I consider this guy, for example, alpha g1 plus 1 minus alpha g2? Well, clearly, this guy's going to be a subgradient also, right? Because if I just take f of x plus this thing, 1 alpha g1 plus 1 minus alpha g2 transpose y minus x, right, then I can write that as 1 or alpha times f of x plus g1 transpose y minus x plus 1 minus alpha times the analogous thing for g2. Right? Each of these is less than or equal to f of y. So the whole thing is less than or equal to just f of y. Right? So pretty trivial proof there. But it tells us that the subdifferential is always a convex set. It's actually a pretty useful fact. We'll come back to that in a second. It's non-empty for convex functions. We already know that because subgradients always exist, but it can be empty for non-convex functions. These are just kind of another way of saying what we already know, we already learned. If f is differentiable at a point, then its subdifferential contains only one point, and that's the gradient of f at that point x. And conversely, if the subdifferential contains just one element, g, then we know that f is differentiable at x and g is its gradient. So just repeating things we already know, but saying it a little differently. So here's a connection to something we've already seen, and this is going to also pop up a little bit later. Let's try to characterize the subdifferential of an indicator function. So the indicator function is a function that if you give me a convex set C, it's attached to that set. So it's defined in terms of that set. And it's 0 when I observe an argument that's inside the set and it's infinite otherwise. So it just tells me whether or not the point x is inside C or not. So I claim that the subdifferential of an indicator function for a given set C at a point x is the normal cone to C at the point x. Right? Where we remember that if you give me any set, then the normal cone at x is the set of all vectors g that have the maximum inner product with x compared to any other vector y that's in the set. So if I look at the inner products of g with elements of the set C, then that inner product is made largest at the point x. That's what the normal cone is defined by. So why is this true? It's a very kind of straightforward argument. Let's just look at the definition of subgradients and plug in the indicator function. Right? So we need to know that f of y is bigger than or equal to f of x plus g transpose y minus x for all y. We want to characterize what vectors g make this true at the point x. So we're looking at the indicator function in particular, right? Let's think about two cases. If y is outside of C, then the indicator function of y is infinite. Right? And this was x is in C, so this is 0. And so this is always going to be true. G transpose y minus x is always going to be less than infinity. It's kind of trivially true. So that means that there are no kind of constraints that are placed on what vectors g can be true by looking at g can be subgradients by looking at points y that are outside C. So let's look at the points y inside C. If y is inside C, then we get 0 is bigger than or equal to 0 plus g transpose y minus x. Rearrange that just tells us that, right, g transpose y has to be less than or equal to g transpose x for all y in C. So the set of g's that make this true are the set of subgradients of the indicator function. But that's just exactly the normal cone. All right, so there's a connection to something we've already seen a few times. And you'll see why that's useful in a few slides. OK, here's just a picture in case you forgot what the normal cone was. We've been saying it a bunch, but it also pops up a lot. So figure it doesn't hurt to keep rehashing this picture. So, right, if I'm at, say, this point x, then the normal cone is a set of all vectors g that have maximal inner product with this point x compared to all other points in the set C. And that's actually going to look like, to be fair, the normal cone is actually, if this is 0, the normal cone actually looks like this. It's any vector that points in the direction of x. So it points in this direction, essentially. That's not true. I'm sorry. It has to point orthogonal to the... I just drew it so that it looked like it was true. Let's move x up here and it'll be more clear. So it's any vector that points in the direction orthogonal to x at the boundary. Okay, we sometimes draw it like this just for clarity, but that's actually taking the normal cone and translating it to start at the point x. The normal cone is actually a proper cone. It starts at 0 and it extends that way. Okay, so this is, for example, the normal cone to the set C at the point x. If this was x instead, call this x prime, then we saw this already. The normal cone, you can convince yourself, is actually, in this case, it's two-dimensional instead of being one-dimensional. And it's anything in that region. And again, this, to be proper, the normal cone actually looks like this. It's actually this cone defined down here, but we usually translate it just so that we can visualize it better to lie starting at the point that we're x that we're thinking about. Okay, a bit of subgradient calculus. We had rules for, we've seen these kind of rules before for convex functions. This is kind of an analogous thing in a sense for subgradients. And that is, if we know the subgradients of, say, individual functions, how can we build it up to get subgradients of combinations of functions without having to recheck the definition each time? So here's a few pretty obvious ones. They're obvious once you look at the definition. If I have a convex function f and I ask for the subgradient of a times f, then it's just a times the subgradient of f, provided that a is positive. If a is negative, then this doesn't work because I will make f concave, right? So that's why we're restricting a to be positive. If I have the subgradient of, if I'm asking for the subgradient of the sum of two convex functions, then it's just the sum of their subgradients. Okay, again, if you check the definition, all these things will be immediate. This is about the closest thing we have to the chain rule for subgradients. So the chain rule is, there's not really a very generic version of the chain rule for subgradients, but this is, I guess, the most general one we have, which is that if I have a convex function f and I compose it with a linear function or an affine function of x, so I define a new function g to be f of ax plus b, then the subgradients of g at x are a transpose the subgradients of f at ax plus b. So if you replace a subgradient with a gradient here, you'll recognize that as a version of the chain rule when I'm composing one function with a linear function. That's about as general as we can do with subgradients. Is there a question?
The subgradient is a set actually, right?
All these are sets. That's right.
If I make plus operation between two sets, is it like a pairwise stuff?
Yeah, I mean, if there's, I suppose, yeah, I think I wouldn't use different notation. There's really only one way to interpret it, but I'm happy to write it down. It's just I take every element in A and I add it to every element in B, and that's A plus B. I think sometimes, no, I'm not going to introduce other notation. I'm just going to keep it as a plus. Okay, so this guy is useful, just like the chain rule is useful. This is another pretty useful one. It's how do I get subgradients of maxima of functions? So we saw what happens for two functions when they were smooth, right? We did that one as an example a few slides ago. In general, if I have, say, m convex functions, and I'm taking their pointwise maximum and asking for the subgradient at a point x, then this is the answer. It actually looks complicated, but it's very simple. Let me see if I can rephrase it for you. We're just going to, so I'm at a point x, and I'm going to look at all indices I such that fi is active at x. And what I mean by that is that fi of x achieves the maximum. So it's the guy that's equal to f of x. There could be more than one of these, right? Because at a point, for example, when f1 and f2 are equal, they both were active. On one side, f1 was active, f2 was active on the other side. And I look at their subgradients, or their subdifferential rather, the set of their subgradients. So look at all functions that are active, I take all their subgradients, and I'm allowed to choose any one of those as a valid subgradient for the function f. Okay, so if I take any function that's active, I look at any one of its subgradients, that will be a subgradient of f overall. But what do we know about subgradients? One thing that we knew was that the set of subgradients, the subdifferential, is always a convex set. So actually, not only these are allowed, but anything in the convex hull of these are allowed. Okay, so I know that these are subgradients. I also know that the subdifferential is going to contain their convex hull. So that actually characterizes the subdifferential completely for a finite pointwise maximum. So let's just go back to the case where we had two differentiable functions and make sure this meets what we had before. On the side where f1 was bigger than f2, only f1 was active. It only has one subgradient, and that's its gradient. So there's only one thing in this whole union. And so that's going to be the only subgradient we can take. When f2 was active, it's the same story. When f1 and f2 are both active, when they're equal, then I'm taking the union of the gradient of f1, and I'm also adding to that set the gradient of f2. So those are both valid subgradients. And I'm taking the convex hull of that. That's just the line segment joining f1 and the gradient of f1 and f2, which is what we saw before. Okay, so this meets what we saw before. But this is a more general rule when we have a finite number of functions that may not be differentiable. Okay, even more broad. Now we're getting kind of out there. But believe me, this rule is itself still useful. If I have a possibly infinite number of functions that I'm maximizing over in a pointwise fashion, right? Then I know from our rules about convexity that this function is always convex, even if s is infinite, even if s is uncountable, actually. Then how do I get subgradients for f? Well, it's actually the same rule. Just ignore, I can't really cover it up because it's the computer screen. Ignore this closure for now. Okay, we take all functions that are active, we take their subgradients, we allow to choose any of those, and then we take the convex hull of that. Any of those are subgradients of f at x. But something kind of tricky happens when we're allowed to take the convex hull of a union that's possibly infinite, and that this may not be closed at the end of the day. Okay, so because we know the subdifferential is always a closed and convex set, we actually take the closure and the convex hull of this union. Any of those guys are valid subgradients of this function, which is the infinite pointwise maximum of an infinite number of functions. Now, this is actually only one-sided. It's not an equality. So I've told you that these are all valid subgradients of f at the point x, but there could be more in general. These need not be the only ones. Under pretty kind of standard regularity conditions, for example, if each of these functions is continuous and S is compact, this set, capital S is a compact set, then we get an equality. But actually, I would stress that you don't worry about that at all, because almost always we only need to know what some subgradients of a function, what are subgradients of a function, and we never have to characterize all of them. So there's a difference between those two cases. Some people call the act of kind of finding subgradients of a function weak subgradient calculus. Because in practice, if we're going to run, say, a subgradient method, we only need to find a subgradient of a function as that we're minimizing. And in general, when we deal with optimality conditions, if we can find subgradients of a function, then that's good enough. We never really have to find all of the subgradients of a function, except for in a certain few cases where that's important. That's called strong subgradient calculus. So, like I said, in general, don't really worry about characterizing all the subgradients of a given function, like in this case, or on your homework. In homework 2, we're going to ask you just to find some subgradients of a function. We're not going to ask you to prove that that's all the subgradients. because for our purposes, that's mostly good enough. Okay, so I've just told you a pretty large set of things that are all valid subgradients of this function f. So a very important special case of this is norms, of this guy's norms. So LP norms, we're going to learn this when we talk about duality, but one fact about LP norms is that if I look at the LP norm of, say, Z, and I want to characterize it as a maximum, I can, let me change notation so it matches the slide. The LP norm of x is the maximum over all vectors z that have q norm less than or equal to 1 of x transpose z, where I've chosen q so that it's called complementary or dual to p. So let's just think about the L2 norm, for example. When p is 2, if I'm choosing q to make this true, then I'm also choosing q equals 2. So p and q in that case are called dual. In other words, I said that the L2 norm is self-dual. And I'm claiming that I can write the L2 norm as the maximum over all vectors z that have Euclidean norm less than or equal to 1 of x transpose z. Well, that's clearly true, right? I'm just going to take z to be the normalized version of x divided by its own norm. And I'll definitely get the L2 norm of x out. This is actually true, like I said, more generally for any p that's bigger than or equal to 1. We call this a dual norm characterization, and we'll learn it when we talk about duality. But right now, you can just take this as fact. And this rule up here tells us how to compute subgradients of the LP norm for any p. It tells us that if we want to know what the subgradient of the LP norm is at a point x, the subdifferential rather, then it's let's talk our way through this. I first find all the vectors z that makes this as large as possible. In other words, it makes it equal to the LP norm of x. And then I take their subgradients with respect to x. So what's the subgradient of this linear function with respect to x? What's the subgradient of x transpose z with respect to x? It's just z, right? It's a linear function. It's gradient z. So in other words, I'm saying I'm taking the convex hull over all z such that x transpose z equals the LP norm of x of the set just containing z. It's a little bit convoluted way of writing it. Another way of writing that, that's just all the vectors z that maximize this inner product. Right? Because if anything in the convex hull of this set is going to maximize the inner product with x, also because this is just a linear criterion. So if I have z1 and z2 and they both make the inner product as large as possible, then so is alpha z1 plus 1 minus alpha z2. So in other words, the set of subgradients of the LP norm at a point x are exactly the vectors that have q norm at most 1 that make x transpose z as large as possible. These guys actually make x transpose z equal to the LP norm of x. So if you go back to the L1 norm calculation we did at the start of the slides and the L2 norm calculation we did at the start of the slides, you'll actually see that this kind of shortcut will give us the answer right away. We wouldn't have had to go through the definition. This is, like I said, this is true in general for any LP norm. So it's a nice fact. Okay, so I'm going to give this motivation, and then we'll take a short break. So why are we looking at subgradients? We've taken a pause in our algorithms unit to look at subgradients. And it may not be as exciting as learning gradient descent or subgradient method, because it may not feel like you can go out after today's lecture and solve your favorite problem. But they're very important for two reasons. The first is convex analysis. And this will focus on more and more in the optimality and duality unit. But we're also going to see in this lecture, too, as kind of a preview, there's a very nice optimality characterization that's given via subgradients. And that really goes a long way for us. We'll talk about that in just a few slides. So if we understand subgradients, we can characterize optimality for convex functions. And then these two things we'll talk about later in the course, so I'm not going to really mention them now, but you'll see that they pop up a lot. From an optimization perspective, subgradients are important because if you can compute them, if you know how to compute a subgradient of a convex function, then you can pretty much minimize it. So it's maybe not the fastest algorithm that we're going to learn, but in a sense it's the most broad. And as long as you have a convex function whose subgradients you know, you can minimize it. So if you're willing to wait, you can minimize any convex optimization problem as long as you can compute subgradients. So that should be a pretty good motivation in and of itself. Okay, so I'm going to actually go through this optimality characterization, and then we're going to take a break, because this is so simple, I want to say it right away. For any function, convex or not, any function f, the point x star minimizes this function if and only if 0 is in the subgradient of f at x. At x star, excuse me. Okay, this is very, very simple fact, but it's extremely general. You can see it applies to anything, convex or not. This is called the subgradient optimality condition. So let's prove that. It's not very hard. I have it on the slide, but it's worth writing out. So the definition of subgradients, right? Say at x star, is that this has to be true for all y. That's what makes G a subgradient. Okay, now I'm saying, what happens if 0 is a subgradient? Well, reduces to that, right? It's not really a proof here, that's it. So we've just said that f of y is bigger than or equal to f of x star for all y. So this is true if and only if 0 is a subgradient of f at x star. Now there could be many other points that are also subgradients of f at x star, but as long as 0 is one of them, we know we've minimized that function. And because subgradients are defined for convex functions and non-convex functions, this is true for convex and non-convex functions. There's nothing special here to convexity. This is so broad, in fact, you may think it's useless, but we're going to see in after the break, the next couple slides, that we can actually use it. Just to harp on something that you've seen before, I'm sure, what is this reduced to when f is differentiable? When f is differentiable, it only has one subgradient, right? And we're saying that 0 has to be an element of its subdifferential, and when f is differentiable and convex, the only element is its gradient, so that means that the gradient is 0. Something we've seen a bunch of times before. Okay, so it's more broad than that characterization for smooth convex functions we already know. All right, let's take a couple-minute break, and then I'll show you some examples of that. I got a question about, and I see this question every year, and it's a definite source of confusion. And it's going to come back when we talk about the KKT conditions, but I'll repeat it again. For non-convex functions, gradients are not the same as subgradients. For non-convex smooth functions, gradients are not the same as subgradients. Right? I can have a non-convex function that's smooth. I can have a gradient that need not be a subgradient. So this statement was only for convex functions, right? Because what we knew was that the function is minimized if and only if 0 is in its subdifferential, if and only if 0 is a subgradient. For convex functions, this is the subdifferential if it's smooth. So that reduces to 0 being equal to the gradient. The gradient must be 0 at the point in question. For non-convex functions that are smooth, this need not be its subdifferential. Right? So this is not a necessary and sufficient condition for optimality for non-convex functions. Does everybody understand that? Right? Go back to this example in your mind. Its gradient may be zero at this point, but that's not a subgradient. So that's not necessary and sufficient for optimality. Okay, just to clarify that. All right. let's go ahead and actually do something which is pretty straightforward, but you'll see where the first order optimality condition comes from. You've learned this, I think, second lecture, and we've used it a bunch of times. We know that if we have a smooth function we're trying to minimize subject to the point x lying in C, then we have a necessary and sufficient condition for optimality, and that's this. So the gradient of f at x transpose y minus x is bigger than or equal to 0 for all y. If this is true, then we know that x minimizes the function f. We learned that in the second lecture. We've been using that. We have never proved it. We can actually prove it with subgradient optimality. Right? Intuitively, this says, just to remind you, that if I'm at x and I try to move to y, that's what this term is. Y minus x is in the direction of y, starting at x. And I look at the gradient only goes up along that direction. So the first order information tells me it's not worth moving from x to y. How do we see that this is a necessary and sufficient condition? Well, let's recast this problem in this form. So we're going to look at minimize f of x plus the indicator of x at the point C, right, where this is going to be 0 when x is in C and infinity otherwise. That's the same thing as the constrained minimization problem that we started off with. Now let's apply subgradient optimality. X minimizes this if and only if 0 is in the subgradient of the sum of these two. But subgradients of the sum of these two is the sum of their subgradients. Okay. We learned what this was actually a few slides ago. That was the normal cone. So I'll write that as the normal cone of C at the point x. And if f was smooth, then this only contains one point. Since we're assuming f is convex, this contains the gradient of f at x. So in other words, we said that 0 has to be an element of the sum of those two sets. Another way of saying that is that the negative gradient has to lie in the normal cone at x. What was the normal cone? Remember, it was the set of all vectors whose inner product with x was maximal among all their points, say y, in the set C. That means that minus f of x transpose x minus y has to be bigger than or equal to 0 for all y in C. This is the definition of the normal cone. And let's just rearrange that. That tells us that f of x transpose y minus x is bigger than or equal to 0 for all y in C. All right, we've actually, in a few lines, just proved like a very fundamental thing that we learned. And I'm guessing that if I asked you to prove this, say on lecture 2, you would have, thought about it for a little while, you wouldn't have guessed that the proof was this easy. But it's an example of how useful the subgradient characterization is for optimality. Any questions about that? Let's just be a little more general and suppose that we didn't assume that f was differentiable. Then this would have been the characterization, right? For some g in the subdifferential of f at x, for some subgradient. It would have been the same argument would have given this. So this is actually necessary and sufficient for optimality for any sum of a convex, possibly non-differentiable function and an indicator function. This is, we talked about before, this is the most general form of a problem that we can consider in optimization, in convex optimization. The criterion is convex. I'm not assuming it's differentiable. This C could encapsulate all of the constraints we apply. This could fold up into it, right? Gi of x less than or equal to 0 for all I, and hjx equal to 0 for all j. we could fold that all into the set C. And so this is the most general representation. This is the most general problem form that we can consider. So we have a necessary and sufficient condition for optimality for any convex problem. Look at that, right from subgradient optimality. That's it right there. Unfortunately, it's not that easy to use in general. That's why this is not the end of the course. Otherwise, you guys would walk away with this and you'd be able to at least analyze most problems. It's not that easy to use. What we're going to see later is something called the Krush-Kuhn-Tucker conditions, which can actually be proven from this line here, that are much easier to use. They're an equivalent set of statements to this one subgradient optimality characterization. These are easy to use. We'll learn those later. Okay. We have about 20 minutes, and we have, I think we can make all examples. So let's go through, we're just going to go through 3 examples now of subgradient optimality, and then we'll call it a day. The first is for the lasso problem. This is a problem you guys have seen a couple times. You'll see this on the homework, I believe. Maybe not. Something similar to this in the homework. And it's, variants of this are used all over for sparse estimation. So replace this least squares loss with your favorite loss function, like, say, logistic loss for classification, or Poisson log likelihood to model count data, or whatever else, whatever your application is, put your favorite loss in. And by adding an L1 penalty, kind of in the appropriate way, we can get a sparse estimate rather than a more classical one where there's not any sparsity induced. So we're in a setting, let's suppose, where we want to do regression. So we have a response y and predictor variables x. Each column of x is a predictor variable. Remember, this is the lasso problem. Minimize the least squares loss of y on x beta plus an L1 penalty on beta. And this lambda is a tuning parameter. The larger we make lambda, the more zeros we get in the solution, beta hat. So subgradient optimality tells us that we have a solution, let's just call it beta, to the lasso problem, if and only if 0 is a subgradient of the criterion at beta. So again, a subgradient of 2 functions, right? The subgradient of 2 functions is the sum of their subgradients. The first term is differentiable. So this is just going to be, if f of beta is least squares loss, then you guys should all know, and if not, you should memorize this, or by the end of the course you'll have it memorized, possibly even get a tattoo with this on your arm, that the gradient is minus x transpose y minus x beta. Okay, we use that all the time. It's just like taking the gradient of a quadratic form. That's the first term. The second term is, remember, it's the subdifferential of the L1 norm times lambda, since lambda was positive. That's one of our rules. We can pull it out. So another way of saying that is that the gradient, I'm just going to try to keep this a little more general. Suppose that f was your loss function. That third line is saying that the gradient is in the subdifferential, the negative gradient is in the subdifferential of the L1 norm at beta times lambda. And we can write that as, say, lambda times, actually it's easier to write lambda times v. For some v that's a subgradient of the L1 norm at beta. What do the components of v look like, right? We know this one already. Vi is going to be equal to 3 things. It's going to be plus 1, minus 1, or anything in between minus 1 and 1. If beta I is positive, negative, or equal to 0. Okay, so the negative gradient, or the negative, the negative gradient, the ith component, can either has to be either lambda if beta I is positive, minus lambda if beta I is negative, or anything between minus lambda and lambda, because I'm multiplying by lambda in front here, if beta I is 0. Okay, applied to the L1 norm, that says that xi, so let me, where's my eraser go? write that down. So the negative gradient in the ith component has to be equal to the sine of beta I when beta I is not equal to 0 times lambda. And otherwise, it has to be anything in between minus lambda lambda. Just another way of writing that. Okay, so this was the subgradient optimality characterization for minimizing f of beta plus lambda L1 norm of beta. Okay. Let's apply that to this problem where this is the gradient. Right? If we think about what's the gradient of what are the components of this, which is the gradient, then they're just given by taking the ith column of x, say, and multiplying it by y minus x beta. So that's what I've done here. I've said that the ith component of the negative gradient, which is xi transpose y minus x beta, has to be equal to the sine of beta I if beta I is non-zero. Otherwise, it has to be anything in between minus lambda and lambda when beta I is 0. That's just this rule applied to the least squares loss. So unfortunately for the lasso, these don't actually lead to a lasso solution. We can't actually look at these and then write down the lasso solution analytically. If that was the case, then I think that a lot of the research that's been done on lasso would not exist. And the lasso would be a lot less interesting in a sense. But they do provide a very useful characterization of the lasso solution. So for one, they tell us how to check lasso optimality. If somebody said, hey, I have a lasso solution, we can actually check these conditions, right? Look at the residual, y minus x beta, take its inner product with every predictor variable, and make sure that when the corresponding component of beta is non-zero, we have to have a lambda inner product between, if beta I is non-zero, then xi transpose y minus x beta has to be equal to the sine of beta I times lambda. So that means that if we think about this as a correlation, the correlation of a predictor, say the ith predictor with the residual, has to be equal to lambda when the ith component is non-zero. The correlation has to be equal to minus lambda when the ith component is positive and then negative. And this is saying that if we set the ith component equal to 0, then the correlation has to be anything in between minus lambda and lambda. So we can actually check optimality using this set of conditions. It's also useful for understanding the lasso estimator. And we'll do some stuff later on where we talk about screening rules, for example. One thing you can do from the subgradient optimality characterization. But what you can see here is that if you have a lasso, so if you know at the lasso solution that the correlation or inner product of xi with the residual is going to be strictly less than lambda in absolute value, then you know that at the solution you're going to have beta I equals 0. Right? Because the only way that this can be strictly less than lambda is if beta I was equal to 0, looking back at these optimality conditions. If beta I was non-zero, then it's going to be equal to plus or minus lambda. So this tells you that you have if you can figure this out ahead of time, then you don't have to, for example, even include xi in the optimization because you know that beta I will be 0 at the solution. That's something called a screening rule we'll learn later. Yeah.
Is beta here necessarily unique?
Well, why don't you tell me?
Sorry?
I said, why don't you tell me? What do you think?
Yeah, I think we should.
Okay, so what do we know about, let's see if we can recall. What's a sufficient condition for uniqueness of a optimization problem? Strict convexity, I think I heard that, right? Okay. Is this a strictly convex function? Is the L1 norm strictly convex? This is strictly convex if at least one of these is, right? If they're both convex and one is strictly convex, at least, then their sum will be strictly convex. You can see that from the definition of strict convexity, right? If they both have a less than or equal, a less than or equal to, and one of them has a strict less than, then their sum will have a strict less than. So this is not strictly convex, the L1 norm. You can see that right away from 0, it's just linear. So it's not strictly convex. How about this guy? I think we even did this example at one point. What's its second derivative, for example? It's Hessian. X transpose X, okay? So is that strictly positive definite? And it might not be, right, if p is bigger than n here. If I have more features than I do observations, then this is not, then X transpose X is not strictly positive definite. This is not strictly convex. This is not strictly convex. So the answer is, in a sense, no, not in general. When the number of features is larger than the number of observations, it's not unique. Okay, one thing that we'll learn later on, actually, though, is that maybe I'll put this in the homework. It's actually not very hard to prove. The signs of solutions are always uniquely determined, and the residual is always uniquely determined. So this set of rules is really well specified. So even though beta may not be unique, X beta is always unique, and so are the signs of beta. It's a good question, but this rule, this subgradient optimality calculation is really well defined for that reason. Okay, let's do one that we can actually. We're gonna see if I. Okay, we'll go through this one kind of quickly, and if you're unsure about it, then just go through it on your own after class. Let's do a version of the lasso problem where we don't have a predictor matrix. It just has identity matrix for X. Then this is sometimes called a signal approximator problem because we have a signal Y and we want to approximate it with a vector beta. So this is a very simplified version of the lasso, but I claim that we can solve it directly using subgradient optimality, and that the solution is actually just taking Y and soft thresholding its components. And that means at the level lambda. That means that if yi is bigger than lambda, we just subtract lambda from it. If it's smaller than minus lambda, we add lambda to it. And otherwise, we just set it equal to 0. So the picture is like this. If this is yi and this is lambda, then when yi is bigger than lambda, right, the soft thresholded version of yi, it just looks like yi minus lambda. That's not the right picture. Okay, because when yi is equal to lambda, we should get 0. Otherwise, we set it equal to 0 for all lambda in between minus lambda and lambda. And when yi is smaller than minus lambda, we add lambda to it. Okay, so if we observe yi in the ith component of y, then the ith component of the solution, I'm claiming, is just going to be the soft thresholded version of yi. So how do we prove this? From our last slide where we talked about lasso optimality, we saw that necessary and sufficient conditions for beta I, or beta, to be a solution are that the residual, it was really actually X transpose the residual, but X is the identity matrix here, is equal to lambda times the sign of beta I when beta I is non-zero, and otherwise yi minus beta I is less than or equal to lambda. So now we're going to actually plug in for beta I the soft thresholded version of yi and just check that these are satisfied. If we can check these are satisfied, then we know that we have a solution. So let's do that. Let's suppose that beta I was equal to taking yi and soft thresholding it by lambda. So let's just think about a few cases. If yi is bigger than lambda, for example, then we're going to take beta I equals yi minus lambda. And so then let's just look at these conditions. If we take the residual yi minus beta I, then that's going to be equal to lambda, which is equal to lambda times the sign of beta I, right? Because beta I is positive in this case. If yi is bigger than lambda and we subtract lambda from it, it's still positive. So we've checked for optimality in the ith component. Right? These are necessary and sufficient conditions. We've just satisfied them. If yi is less than minus lambda, then there's a similar argument. And if yi is in between minus lambda and lambda, then remember the soft threshold aversion sets beta I equal to 0. And so what's yi minus beta I? In absolute value, say it's just equal to the absolute value of yi. And we're only setting equal to 0 when it's between minus lambda and lambda. Well, so by construction, this is less than or equal to lambda, and we've again satisfied these optimality conditions. Okay, so if you wrote down these optimality conditions, I'd say case by case, and you thought, what value of beta I is going to make these satisfied, you would see that you should take the soft thresholding function. So go the other way as well. But for the sake of time, I just said, here's a solution, let's just check it. Okay. I at least want to get to some part of this. We only have about 5 minutes left. But this last one is a nice one. It's pretty different from the other ones, so I wanted to get to it. I may have to finish next time. But let's think about I have a convex set C, and I'm looking at the distance function of a point x to C. So this is equal to the distance between x and C. And we're going to call this u. Okay, u is going to be equal to the projection of x onto C. This is convex. We actually know that this function is a convex function from one of our previous classes, from our rules. And now we want to compute its subgradients. So first of all, we're going to note that we can write the distance between x and C as just x minus its projection onto C in Euclidean norm. Okay, that's really just the definition of its projection. It's the point that makes this true. And for a convex set, this is actually uniquely defined if C is convex and closed. So we can always do this. I claim that when the distance function is bigger than 0, so when x doesn't lie on the set, essentially, that the subgradients of the distance function are just, there's only one of them, and it's what happens when I take x minus its projected point and I normalize it. i.e., this is its gradient. So this would be a case where actually, if I asked you on say a midterm, or you encountered another class, the question, is this differentiable? Is the distance function to a set differentiable? That might seem like a pretty tricky question. We're not telling you the set is smooth. We're just telling you the set is convex. So this might seem like a pretty tricky question. Once you know subgradients, you can go ahead and you can write down the characterization for subgradients. You'll find out there's only one element in the subgradient. Therefore, that's its gradient. So this is a neat way to prove that a function is differentiable also. In this next few slides, and also because we're running short on time, I'm just going to only prove one direction. I'm going to start proving one direction. I'm just going to prove for you that this is a subgradient of the distance function. But you can see from the arguments that they actually go the other way as well. In fact, you can just kind of retrace the steps, and you'll be able to prove the other direction. So we're right at the end. Let me just draw you the picture, see if I can give you the proof by picture. And then we'll prove it next time. Okay, so a necessary and sufficient condition for optimality right? We're going to write down a problem, and we're going to apply the subgradient optimality of that problem, where we're going to think about minimizing over all points, say u in the set C, y minus u squared. That's a perfectly well-defined convex optimization problem. The solution to this, right, solution is, by definition, this guy, the projection of x onto the set C. So we're going to use subgradient optimality, first of all, for this problem. We've already seen this before, I think, in an early lecture, to get a characterization for u that tells us that if I look at the vector from x to u, and then the vector from u to y, say at any other point y in the set, these two have to have a positive inner product. Something we learned before. And that tells me that actually C is contained in a half plane of the set of all vectors that have a positive inner product with u minus x. Right? Because it's true for anything in C, so it's definitely contained in this half plane. Okay, and then the intuition is essentially that from this we can rely kind of on a geometric characterization of this half space and its relationship to subgradients, which we'll bring up, to prove that this distance function always lies above kind of a canonical distance. So the distance function of x to the set C is always going to lie above the distance from x to the half space, right? Because the half space strictly contains the set. And the subgradient characterization, right, has to tell us that f of y is bigger than or equal to f of x plus g transpose y minus x. So we're going to be able to get this part less than or equal to a quantity involving the half space, just from a very simple geometric argument that I guess I'll draw for you guys next time, and that'll immediately give us the subgradient characterization for the whole set C. Okay, so I'm not sure if that conveyed much intuition, but it doesn't really matter because next time we'll do it on paper anyways. So I guess I will see you on Wednesday.